Hello, everybody. This is Mr. Lim. We haven't discussed how to solve the problem related to sum to infinity, right? So let's look at this question. Find the sum to infinity for the following series if it exceeds. So it means that not all geometric progression consists of sum to infinity. Not every geometric sequence has sum to infinity. For example, give me 1 minute. Let me adjust this to the slide I want. Okay. For example, let's say we have this geometric progression. This is the geometric progression: 2, 4, 8, 16, and 32, and so on. This is a geometric progression. This geometric progression consists of A equal to 2 and the common ratio 2, right? So why not we try to find the sum to infinity for this case? Sum to infinity is A over 1 minus R, if you remember the formula. Okay, so my A is equal to 2. My R is also equal to 2. So I have 2 over negative 1. I got negative 2. Imagine the sum to infinity is 2 plus 4 plus 8 plus 16 plus 32 and so on and so on and so on. All these are positive value. If we add all these positive value until infinity, how do we get negative 2? It is impossible. So for your information, this case, this geometric series, we do not have sum to infinity. Or in other words, this series diverge. All right. As a result, for all these geometric series, not all consist of sum to infinity. In other words, not all series converge. So what determines whether a series converge or diverge? The key is this: modulus R must be lesser than 1. If this scenario, holds, then the sum to infinity exists. Okay? And the series converge. Otherwise, the series will diverge. The sum to infinity doesn't exist. Okay, so let me erase all this because I need space to write. Okay, if you want to copy, just pause the video and copy the things I write. Okay, so I'm going to erase all this because I need space to write. Give me 1 minute. Yep, let me erase all this. I need time. I'm so sorry. Okay. Yes. Now, let's look at question A. Question A, we must first find the common ratio, right? So the common ratio in this case is 3 over 2. 3 over 2 is 1.5, isn't it? So the sum to infinity doesn't exist because the modulus R is greater than 1. So how to write? We have to write that since modulus R is equal to 1.5, which is greater than 1, okay, the series diverge. The IVERGE diverge. It means the sum to infinity does not exist. Okay? So question A, we no need to find the sum to infinity because it doesn't exist. Question B, can we find the common ratio? The common ratio is equal to negative 1 over 2, right? So modulus R is equal to half, which is less than 1. In this case, the series converge, right? So the series converge denoted that the sum to infinity exit. So if the sum to infinity exit, we must find the sum to infinity, right? So S infinity equals A over 1 minus half. Sorry, it is negative half. Let me erase this. Negative half. I need to change that to negative half. So I got 2 over 1 plus 3 over 2, which is equal to 2 over, oh, sorry, I make a mistake here. This is 1 over 2, 1 over 2. So I got 3 over 2, and then the final answer is 4 over 3. Okay, so I have done A and B. Try C on your own. Okay, try C on your own. Okay, next, let's try this one. Question 2, revision. For a geometric progression whose first two terms are 5 and 0.5, state with a reason why this series converge, and hence determine the sum to infinity. All right. So this question has given you the first term and the second term, the first two terms, right? So T1 equals 5 and T2 equals to 0.5. So state with a reason why this series converge. It must be related to the common ratio R, right? So R equal to T2 divide T1, which is equal to 0.5 divide 5. So I got 0.1. So since your modulus R is equal to 0.1, which is lesser than 1, the series converge or diverge? Converge, right? Converge. So if the series converge, definitely sum to infinity exit. And then we have to find the sum to infinity. So sum to infinity is equal to A over 1 minus R. My A is 5. My R is 0.1. So you should get 50 over 9. Okay. So maybe we can try one last question. Okay, let's try this one. A geometric series has first term A and a common ratio R. Show that the sum to infinity is this one. Okay, so I know that sum to infinity is equal to A over 1 minus R. Okay, so this is my answer, but this should not be your final answer because the question wants you to show that this, your sum to infinity, is equal to this one. All right, so we need to simplify this. So I can write this as Z2 over Z2 minus 1 over Z2, right? And then I further simplify this. I got A over Z2 minus 1 over Z2. And then I can write it as A Z2 over Z2 minus 1. Okay, after you have got this, we can see that this is still not equal to this one, right? They look very different. So I need to erase, if possible, erase this denominator. How to erase this denominator? Or maybe I need to do something to the denominator? Yeah, what I should do? The answer is I must multiply with the conjugate. So let me continue here. Yeah, my A Z2 over Z2 minus 1, I multiply with the conjugate. So I multiply Z2 plus 1 over Z2 plus 1. All right. So why do I need to multiply with the conjugate? Because, okay, we can do that at the side. Let's do this at the side. Z2 plus 1 multiply with Z2 minus 1. Okay, we expand this with rainbow multiplication. We got 2 minus Z2 plus Z2 minus 1. And then we got 2 minus 1, which is 1. So you see, my denominator, as if I multiply them, my denominator becomes 1. right? This one, we have a denominator of 1. So we have already kind of like cancel the denominator, or maybe like abolish or make the denominator disappear. Okay, so now we have a Z2 times with Z2 plus 1. Okay, we multiply this, we got A2 plus Z2, and then we got the answer shown. Okay, so again, if you have any question related to the slide, please make appointment with any of the mathematics lecturer. Thank you very much. Bye bye.